All right, we are live for day 8 of Advent of Code 2023 with 10 minutes to spare. So, not a lot of time for warm up today, but we could do a little bit of a review. Um, so, quick recap of yesterday. This was the not quite poker hands problem, and it turned out it was easier than sorting normal poker hands, and I made it harder by not realizing that the rules were different. But basically we sort first by the hand type, and then the secondary sort is by just the cards themselves in order. Um, these orderings come right by directly from finding the enums, and I could just give it by the ordinal type, right? So 5 kind is assigned an ordinal type of 0. They'll be prioritized before all of these others are listed. Same with ace up here, beating everything down to a 2 and joker. Um, So the meat and potatoes of this problem was this choose hands method here, which assigns hands a hand type to these cards. And what I first do is I group these by the counts, the amount of them, as well as the types of the cards. Right, so I sort those, and here I just sort of match over them explicitly, right? So if we have a group, one of these group types has a count of 5. This whole idiom here is just to count, match every card type to its full count. It's not very legible. It should be at this point. I use this so often. This should be built into standard library, but it's not for some reason, like it is in Python. But this allows me to match over these fairly explicitly. So the structure here is fairly apparent. We have 4 of one card, we have 1 of another. If that other card is a joker, then we actually have a 5 of a kind instead of a 4 of a kind, and etc. So forth down the list. And yeah, there we go. Those are all already sorted out. Um, one thing I didn't realize was that these are actually already sort of sorted. If I do sort them by the count, by the counts, these will actually go in order already. So the same order that I've given it is the same order that these would come in. So there's no need to match on these explicitly. I think it's easier to think about, especially once you bring in jokers and think about what each of those joker cases can become. Like 2-pair in particular, it become a 2-pair, full house, and 4 kind. And then when you're debugging later on, you can browse through the output and actually see what's here, right? Like the list of all the cards you had in order. That's not formatting well, but you get the idea. Um, anyway, I mentioned that not because I thought about it, but because Nikita, who I don't know if he's here now, but he showed up last night and he posted some of his code to Discord, so I want to highlight that. How do we do this here? Yeah, so this is a Python solution, and Python has counters, which I really like. So this does exactly what this group map reduce over here. My code does. Let me pull that up. This whole thing, right? It makes a map from everything to its counts, and it's also like mutable, so you can keep adding to the counter, um, and that works pretty well. And here's what I noticed. So for hand type, so part 1 key hand type. What is the type of this? Anyway, it is these sorted. It shows first the um it's sorted by the counts, which will just naturally a list of like 3, 2 will be beaten by a list of 4, 1 in like a natural sorting of a list of numbers. So Nikita is leveraging that, and I think that's a great insight. That makes it a lot faster to write this, and maybe even not necessary to debug. I say that this is easy to debug, um, but then again, like this needs no debugging at all, right? If I write a mistake in here, this gives me more room to write mistakes. So that's a point for nice code there. Very clean solution. I do like this. I don't quite understand how this works with the jokers necessarily. Jokers counter J. I would have to look at that a little bit closer, and we might be, well, we have about 4 minutes. I don't know. So hand type sorted. This looks like the same code so far. Counter of the hand values. So counter is separate. Counter, we start a separate collection of the counter hand. And then joker, we delete the joker. Do we add something back to the counter? Oh, I can't do Control F here. So we count the jokers. We add the jokers somewhere here. The hand type. Oh, so like whatever the largest one is, you just add the jokers. That makes perfect sense. Yes, it does exactly that. Let me think about that. That's not something I realized in the moment yesterday. But yeah, you would always add it to the biggest existing group because this is essentially like biggest existing group, and if there happens to be a second group, that basically is just a tiebreaker over a different pair. Like these both have pairs, except for the case of like all 4 kind of beats full of a house. Well, house beats 3 of a kind. Yeah, yeah. I guess that works. Yeah, I mean these really just are sorted by that. Um, which means adding to the largest group is always a good solution. That's perfect. That's excellent. That's a nice trick. Okay. I'm gonna react to that with like a star. And maybe I'll apply more. Let's say. Really nice insight. I do appreciate this. Okay. Well, that's that for now. And at this point, we should get ready. Um, welcome, by the way, Zaron. Zaron. Good to have you back. Okay, problem is out in 1 minute. I might look briefly over the leaderboards, maybe have some goals here. Wow, I've fallen quite a bit behind. There's a gap here. There's quite a gap between 6 and 7. I'm not gonna make that up today unless, someone up here really chokes today and falls behind a lot of people. But perhaps on the Scala leaderboard, there's some redemption to be had. I'm in second, but a 9 gap is gonna be hard to fill. Um, but we'll see. We're not really here just to compete. It's also a lot of fun. Oh, my day 8 worksheet ready. Day 8. Delete stuff. Change that to 8. And a problem has dropped. Let's read it. Okay. And input, this is interesting. So we're going to parse three. This is going to turn into like a map of some sort. Left, right, left, right. Okay, interesting. Haunted wasteland. On the camel's patches is labeled maps. Sure enough, it's full of documents. Your puzzle input about how to navigate the desert. Okay. The document seems to contain some sort of network. We might have a Dijkstra or some sort of search prompt today. You're meant to use left and right instructions to navigate the network. Excuse me. If you had the camel follow the same instructions, you can escape the haunted wasteland. After examining the maps for a bit, two nodes stick out. Triple A and triple Z. That must be A is where we are right now. Z is our goal. Okay. What defines each? Okay, let's get this example. AA, you need to look up the next element based on what. So if we're told to go right, then we go to BB. Okay. And when we follow those instructions, so what's the goal? We might not find ZZ right away. If you run out of left-right instructions, repeat the whole sequence of instructions as necessary. Okay, we can repeat them. Here's a situation that takes 6 steps to reach ZZ. Starting at AA, follow the left-right instructions. How many steps are required to reach ZZ? Okay, so we'll parse this into a, into a map. And looking at this, I think we can just go through them one by one. No need to have references. So we'll get the directions. Try on the first line. So val directions equals input dot head, and then we'll do input dot drop to and parse these. Input dot drop to dot map, or we can fold this. So dot fold left. You start with a default value, a map dot empty of string to a tupeless strings, I suppose. Yeah. String to a tuple of string and string. Okay. So we have our map and we have this. It wasn't able to anticipate what the parsed input would be, of course. That's totally reasonable. It's gonna be a string of some sort, start and left and right. I'll just name them start equals left and right. And then map.updated b.reverse makes no sense here. None of this makes sense. So we update left, or rather start with left and right. Good morning. Worst thing about AOC is actually stand up at 6 a.m. Yes, stand up at 6 a.m. being ready for code before your first coffee. Wait, is it 6 a.m. for you right now? And you have stand up at the same time as advent of code? That's unfortunate. Okay, so this is our map. I'll call it an adjacency map, so I'll just call it edge. And we can look at this. Oh, this should be lowercase. Okay, edge for each print line, just to make sure this makes some sort of sense. I don't know why it's not running right now. Right. Oh, there's a dollar in here. There we go. Okay. And now we navigate. So, Germany time. Okay. So you are plus 6 hours from me, which puts you at 6 a.m. Exactly. But why are you working at 6 a.m.? Stand up. So we can do this a step at a time. There's our current location. We'll say move. And then we have our current position, which is a string. And then direction, which is a character. How did it know? Because directions is a string, I suppose. Vowel left, right. It knows. It knows. Okay. And then now we take the directions and we repeat them. And we're going to have at some point like an iterator over the move. Okay, if this is an infinite thing, what are we going to do? Are we gonna scan, or are we gonna? I think I think we can unfold with state of some sort. Yeah. So I'm gonna make an infinite directions val infter equals yeah, I'm gonna do directions. We're gonna turn that into a lazy list and then cons it onto itself. So we're gonna make this a lazy list of characters. And when I do this, apply it to those elements. Um, and yeah, okay, that should work. I should do a test. Let's say val equals RLLL, or rather directions. There we go. And let's do infter dot take 10. And what is that? That makes string. RLL, it did not complete. Oh, yes, of course, we have to loop it onto itself. RLL, RLL, RL. Okay, great. So we have infinite directions. And now we can do an iterator dot unfold with state, or do we just do an iterate? To do an iterate, we would have to take, so we have the adjacency graph. We'd have to have a function that continually operates and returns the same type of thing. So a function that takes, oh, what am I thinking here? Our current position and the current state of our whatever. We can do an unfold too. So iterator.unfold. And our state is infter. So these are our directions. And then we have our position, which is AAA string. The case pause dir onto the remaining dirs exactly. And it's always going to be a sum. Next pause equals move pause dir exactly. Wow, it got that autocomplete exactly right. It's returning this position. Next pause dirs. Okay, so we have val positions. We have an infinite list of or like an iterator. Could be a lazy list. And we can do positions dot index where equals z. And I don't know if this will be an off by one. So let's start with AAA. I don't know exactly. So starting, how many steps? So 0 steps to reach A, which makes sense. So this would give us 0, right? So if we just do in ZZZ, that will be the correct answer. Val ands equals positions index where equals ZZZ. Oh no. Running for 7 seconds already. That seems like a bad sign to me. Yeah, it seems to be going in an infinite loop. Okay, let's try this on the test input. So they 08.text 2023. Let's save that as an example, dash x, and we'll use this example here. Let's see if we get the right answer for this. This is just going to be right, left, right, left, right, left. No. But what we can do, so we're going to do like positions that take 10. And at each step here, let's do some printing. So print line position. Okay, so we are at pause going dir. Yeah, at pause going dir. That to list. And we can see like the first 10 moves. So at AAA going right, going left, left, left. Why would we go left 3 times in a row? Right here, wait, dirs. So we use the dir, right? We use the dir, and then we do the tail dirs. Oh my God, that's what's wrong. Up here, when I'd written this test input, I forgot to unwrite that. Now this should be back to whatever it's supposed to be. And now this will make more sense, and it should complete. I'm going to turn this positions into def so I don't accidentally spend an iterator when trying to write my answer. 17263. Okay, 17263. There was no issues with the solution. I just need to fix my input. Continue part 2. That was an easy problem, but I don't feel like I was fast. So I'm 3000 for that one. At least it was smooth. Let's go part 2. Now, it's going to take significantly more steps to escape. What the map isn't possible, but isn't for people. What if the map is for ghosts? Ghosts, even bound by the laws of space-time. Only want to find out. Wait, what? Examining the maps a bit longer. Let me put myself behind. Your attention is drawn to a curious fact. The number of nodes with names ending in A is equal to the number of nodes ending with Z. If you're a ghost, you'd probably just start at every node that starts with A, all over the paths at the same time until they all end up at Z's. Okay. Okay. 11A and 22A are starting nodes, right? Because they both end with A. We simultaneously navigate. So now, instead of a position, we have a list of positions. So this move function still works, but now we have to apply it to a list of positions. We're going to call this positions multi. I'm just going to write a new version of this function, and this we'll just save it as ans1. So positions multi. So val starts equals, we just need everything that starts with A, so edge.filter. Almost, we want, no, not even close actually, edge.keys dot filter that ends with, it somehow knows what it ends with, but it's not with a 0, it's with an A. Okay. Edge.filter ends with A. And this is an iterable. I'm just gonna to list that. Okay, and then now we can start with starts. And this is now plural. We're just gonna say pauses. That's awkward, but we can remove this print line. And then next pauses, I suppose at this point we do like pauses.map and move in that direction. And then we had the next pauses. And oh, you know what? This is probably not going to work. I mean, it's probably going to work technically. We're probably going to like have to find a period. Yeah, we're going to have to find a period. And then like use Chinese remainder theorem, I think. So, I mean, we can do a test that this works logically with the example. I'm not going to try it first on the main input because I don't know how many of these end with A. We can do a quick check. So starts.size. Let's comment this for now. Starts.size. Wait, one. Okay, I thought we took the keys. Ends with A. We said everything that ends with A. Edge.keys. What are the keys? A lot of things. Oh, wait. This is still the test. Oh, and it's a bad test. We're gonna do this one here. So let's save this as x2. Okay, now this one will have multiple. Yeah, sure. We're gonna go ahead with testing it, even though I know it won't work. So we have remaining durs, next pauses. Exactly. And now ends to equals position built by that index where not contains, but all of them end with z. So for all dot ends with z. And this won't be performant. In this case, it gives the answer 2, 2, edge.keys. Wait, are we still using the old? Oh, right, we are still using the old one. Okay. Let's comment out part 1 because it's not going to work here. And we get, yeah, we get the answer 6. Okay, let's change back to the normal input, and I'm gonna have to cancel that run. Def position. I'm making assumptions about periods right now. So we have to look at those z's. I want to do some research here and see where the z's go before I make a claim about periods. So edge dot keys. My filter ends with z dot to list. Oops, edge. Okay, so starts at size is 6. There's 6 starting. Oh, wait, there are only 6 starting areas, and this is with the main input, right? What are these? FTA, CBA, Q&A, Q&A. Okay, 6 is not too bad. Yeah, and how many Z's are there? So let's do a dot size here. Yeah, of course there are six ends as well. And where do each of these go? So edge dot, we're just going to filter on the things themselves. And we're only going to do that filter on the key, enter z, dot to list, reach print line, and they go to our, a lot of other things. What I can do is say do positions. Oh, and here's the thing about periods here. This string, even if that did repeat at some point, the string is going to have its own period. So it'd have to be like some multiple of this as well. Navigate from both nodes, Repeat the process until all nodes are at Z. If only some of the nodes are at Z, they act like any other node and you continue as normal. So left on all the paths, right on all the paths. 11B goes to 11Z. It's all a thing that's not ready yet. 11Z will go back to 11B. Oh, interesting. That does loop back into itself. I think what we need to do is for every element in this map, we need to count how far away it is from a Z, perhaps. This is a case where it'd be nice to have my pen ready, but I don't have my pen ready, so I can draw on screen. So let's think about this. We have let's say we know all the Z's, and or let's say we know all the locations and we know how far any of these locations are from a Z. Um, well, I mean, again, that's going to be hard to do because you can't predict that. How far away is from a Z depends on where we are in the cycle of left-right directions. So that doesn't quite work either. Um, you know, like I could let this run. We've tested that this works. I could just let that run in the background while I'm thinking, and like maybe it'll just run for 2 minutes and complete. Uh, but I'm feeling like I doubt that. Um, so this is where all the C elements go after. Yeah, at any point. Um, and are there periods in here? L L R R L. Hmm, how many lines are there? There are a lot of lines. I wish I'd taken that. Hmm. Okay, this is one. This is one to think about for sure. Uh, well, okay. Let's just walk through a scenario. Everything is walking. At some point, something hits a Z, but that doesn't matter because they will have to hit the Z. I mean, what we could do, we could look at the length of these directions, right? And we can. This can be our cycle. So let's say we start at the point AAA and see where it ends up after going through all those directions. And if we do that for every direction, then it's only like something squared, the number of directions times the number of nodes, number of operations, right? And then basically we can have cached for everything where it goes after so and so many steps, right? And then we map our 6 positions and we see if in anything ahead of it there is a whatever. Okay, I think we have our solution here. So I'm going to work on that. Um, so we don't even need this infinite anymore. Um, so def, what did you get so far? I'm confused on part one. You mind pasting it somewhere like a gist? Um, yeah, I can do that. In fact, you know what I can do? I can just commit this and send you to my GitHub. Um, I can do that. So I'm gonna save that. add 8 mit 2023 day 8 part 1 as solved on stream. Git push. And I can give you a link here. AFC GitHub. Oh, you're from YouTube. Aiden from YouTube. It's not every day we see people from YouTube. Okay, so you can see that on my screen, but let me also just type it in here so you can see it. There we go. So that's where you can see my code. And for part 2. So we have all of our starts, but we have to do this for, excuse me, for everything. So we have a new function, and this says, I don't know, this is its path, and this is given a start which is a string, and we want a list of string, or maybe a vector. We're gonna make a vector, and this will be every place that is visited by this path. And yeah, so we can just keep doing our move method. I think this is just a fold left on the directions. So we have directions that fold left, vector start, and then we keep concatenating to the right whatever the move is. Yeah, and we'll do that with all the directions. We add a new piece. And then now we're gonna do edge.map values, and we're just gonna map them. Oh wait, we're not gonna map values. We're gonna take edge.keys iterator dot map, and then this is a start. Actually, yeah, we just map. Well, no. So we have a start, and then we have s onto path, and then we can do to map. It knows what to write. That will never cease to make me happy. No problem, Aiden. No problem. Happy to share my code. Okay, so here, for each of these, we now have a map. Okay, and then now we have our locations, and we keep iterating through these. So val. So okay, we have our starts, and then I don't know, we test. And we will kind of keep iterating. So each of these we sort of transform into its new starting point, which is going to be the end of this vector, right? And then we check. Let's define a check function. And a check will say, given our decisions, we're just gonna keep with this pos word. So given a list of these strings, it's not pause it for it, and then yeah, we check if they have an index, their paths. So we do pause.map This here needs a name. Val cached path. So we map each of these to their cached path. And then we check. Okay, so we have a list of paths. I think what we want to do is we're going to transpose this so that the first element is all of the starts. And then we want the index where they all end with z, if it exists. Okay, so we're going to transpose and then dot index where. How does it know what I was going to write? It's like it's listening to my mic. Val I. And, well, let's see. What we're going to do, let's do this option that when I is greater than 0, just greater than 0. Then we do, this is just going to turn an option of index. When I is greater than 0, we just return I, sure. Oh, this is an int actually. Okay, so we have our starts, and we keep changing our starts, and every time this fails, we keep moving on. So let's do like an iterator that iterates. So our start, um, yeah, we're just gonna keep iterating, and then we're just gonna stop when we get an index of some sort. Yeah. And then for every 0, we just add the length of the thing, or for every none, we just add the length of the direction string. So we start with the starts. And then we have starts, and well, we check the starts. So we check the starts. If uh, yeah, so we check all of those starts, and we're gonna keep iterating no matter what. But we need to have like return value at each point, which will be the next thing. Iterate isn't right because we have some state. Okay, so we have some state, which is our starts. And then we have our steps so far, which is going to start at 0. So we're going to do decisions and then steps. And then option apply. So this whole thing is just going to be it's just going to be a sum actually. And we check the starts. I don't think that actually matters, but it's actually what we'll be returning. So we check starts, and then we move on to the next state, which let's see, let's check starts, which is going to be the last element. So cached path of each of the starts. Starts map cached path dot last. So cached path dot last element. And that is our next state, right? In our unfold, we had the thing we're returning. Okay. And at this point, I just call this states. I'm out of ideas. And then we're gonna span across this. So val, we have a bunch of times that we go through. So states dot span dot non-empty. States dot span non-empty. So this is a non-empty count of where the z is in common. So these are the places where you passed all the way through. Use directions. I'm really not coming up with the best names, but we can clean that up when we're done. And then this is where we found. And then val ans2 equals used dir.size. I want to make this a lazy list. I don't want to deal with the iterator messing things up. So it's going to be used.size times directions.size. I guess these are things where we cycled all the way through. Yeah, sure. Times directions.size plus found.head.size. And found is going to be a sum of something. And so that should at least run. I don't know if we have like an off by one or something here. Let's fix type errors. Oh, this whole thing needs to be wrapped in a sum because we're never going to stop doing that. Okay. Found a list of string. We require a list of string and an int. Oh, right. We had other state here, which is the steps. Oh, okay. In that case, we can do like steps plus. Yeah, actually, this is easier. That's why I wrote steps in the first place. I didn't have to do this kind of silly stuff here and the span here. So steps plus direction dot size, and actually the number of steps depends. Right. So val c equals check starts. And unfortunately, like, yes, this is part of the state. It's not part of what we're returning. Right? Like we can keep. Yeah. That doesn't really help us right here. I'm gonna keep this code. This should run. Found.head.size. It has an issue with this. This it found something onto nothing. What is found? Found is an option. Oh, right. Well, okay, yes. But why is it a lazy list of nothing? Because this is not compiling properly. This being the things we're, oh yes, we need to uncomment that. There we go. C is now defined. And this would be directions.size. And at some point we can refactor this, choose a better loop. But hey, this runs. this runs and gets us a 0. So let's look at this. Used size is a 0. So we're spanning non-empty. So this is a lazy list of option of ints. So the ones on the left will be non-empty. So actually what we want to do is empty. And then found will be the first non-empty one. So now that makes sense. That runs a little bit longer. And again, I suppose while that's running, I could think about how to refactor this. What I want to return, I think, is a sequence of number of steps moved until at some point we stop moving. Yeah. So see, let's check. Oh, another way to write this whole thing here. Oh, you know what? That is not going to stop. We should at least test this on the example. Example 2 rather. Oh no, we can't have you running. Okay. Let's see. In fact, it might very well infinite loop for the example as well. Yeah, I'm going to refactor this. The refactored version will be easier to test. So let's do val states equals lazy list unfold. So we have our state, which is starts and steps. And then we still have the pause steps, yada yada. But now we keep going. So the state steps plus directions dot size. Yeah. And honestly, it's gonna be directions dot size minus 1. That's the max steps to get to end. Or actually, no, we take every one of those steps, so there's no minus 1. Okay, so to the steps, we add the directions dot size. And that for each of these, like move. Why is there a move here? That's wrong. Did you get infinite loop 2? Yes, I did right now. I mean, I do have an approach that I think should be efficient enough. And like one thing I can do is I can sort of cheat. So we have our cached paths, right? So the paths that every one of these takes. And we could look in the cached path for a position where at least 6 of them end in Z. Nah, that shouldn't be necessary. So we move the starts. So it's like starts.map cached path. And then dot last. So the starts have moved, the directions have increased. And this whole thing, how much the directions increase should depend on the check. So it's gonna be steps plus c dot get or else directions dot size. Now steps taken here. Yeah, I'll say steps taken. So steps taken makes it a little bit more clear. Steps plus steps taken. Sure, we're increasing that. And then now I'll pause. And this is if we move all the way. Honestly, what we should do is what we could do will look more clear. So we have to check if C that is defined, and C is rather this is a steps taken. Right, and then where we move here would also depend on how many steps we take. Except at that point, it doesn't matter because all we want here is the steps taken. Um, we could also put like a boolean in what we are returning. That just tells us when to end. I'll do that. I feel like there's something clean hidden here that I'm just not seeing tonight. Okay, E dot is defined, and we're just gonna look for that. And we don't need C. We just need steps plus steps taken, right? And while it would be more correct to like adjust this new positions, val new positions equals this, and it would be more correct to adjust that depending on how many steps we take. But it's not going to matter because at that point we don't care about new positions. And this is just internal state, but we're never going to use anything past that. Wait, so steps taken, new position. We're going to do steps by steps taken as well as C that is defined. And now we take states that index where actually I'm going to do collect first. Collect first case steps true, return steps. That's exactly ends to. Now ends to or I don't know. We just call it steps. Steps and now ends to equals steps dot get. And that's that. I'm going to test on example 2 again, and we should get the answer 6. And there might still be an infinite loop in here. Here's my cached path. So 11z will go 11z, 11b, 11z. It'll eventually go back to itself. So 1, 2, 3, yeah. 2, 2z. Wait. Why is it starting? Oh yeah, we're just doing these for everything. So 2, 2z goes places. XXX goes places. Everything goes 3 places. And is there an next row 3 that might end up being, yeah. For only on nodes that end with Z. And this might end up being a place where we end up having to do, I'm not sure. Gonna restart the worksheets because we might have filled it with a Stack Overflow. I'm not sure. Okay, wait for that to start running. And in the meantime, what we can do is think of ways to be even smarter about this. Um, what we could do is look through different. Oh, did it just shut down on its own? It's updating VS Code server to a new version. Oh, that's annoying. Okay, fine. We'll wait for it and think about it. So we have the cached positions, the place where every point will go if it goes all the way to the end of the left-right cycle. Right. And we could look through those for a set of, what, 6 elements that end in VS Code for the updates. So I'm thinking instead of like continuously going through this, hmm, um, we could cache even more aggressively. So we could cache not just the path, we could cache the indices where it ends up at a z. And then we can cache the final index that it goes to if none of those work out. The val z indices. So cache path dot map values, and then we get all the indexes of all indices. Nope. Where's my real autocomplete? I don't want Chat GPT here, Copilot. I want my yeah, this is not gonna work. We're not gonna let that run. Okay. I need methods. But this is my editor hasn't caught up with me. But we want all indices where in fact we can just look up Scala API. Oh, where is there? It will show up in the same file that has like index where. And then let's see. Indices. I can just filter. Yeah, fine. I can just filter indices. Okay, so we're gonna zip with index dot filter cases where it ends with z dot map to exactly that. Okay, and then val destinations equals cached paths dot map values dot last. And then what's the is this going to be a map still? Have to do dot view. It's a temporary thing. We're deprecating a function dot to map, and then dot to map. Okay, so this can make our search a little bit faster. And assuming there's no like missed logic that is causing us an infinite loop, which I mean that could very well still be the case. We're not going to use this check function anymore. This is too expensive. Yeah, in fact, we're not going to use this old states. Should I just delete all of these? No, I'm gonna reuse part of this code. Um, so yeah, you have steps. There's no longer a C that is defined. So So after each round of steps plus steps taken, once we have all of their positions, and we take the first word, like the final position is all with z's. Yeah, so we can do that. We take the positions, dot map cached path of that position, and then we take steps taken, and this will give us a list of positions. Yeah, and we'll call it new positions. Oh, wait. We no longer have this check here. Or something that. Dash path, steps taken. Yeah, steps taken might just be direction dot sized, in which case. Oh, hold on. Okay, if we have like 5. Cache 1, 2, 3, 4, 5. Cache path. What does it have? Oh, okay, so path. Yeah, it's gonna be directions plus 1. Okay, so directions that size is going to be fine as the steps taken. The new positions, not cached path. Whatever. So steps was tested and new positions. And now this is also our state. So this can just be, it's not even an unfold anymore, it's just an iterate. Iterate starts and steps. And then we just return pause and steps, and then we just keep iterating on that. So new positions plus, yep, this right here. So this is just an iterator, and then we are just going to stop this iterator and take the first index. Yeah. Iterator, not iterate. Now we're going to take states dot select first case, exactly this. So if decisions, they all end with a Z, then we return steps. Steps. And this is exactly ends to ends to equals steps get. And I hope I'm not going in circles. Like this is definitely more performant, but it might be more performant again on like an infinite loop bug that is not going to get us an answer. But let's see if it works with after 6 steps. So if this works properly, then it should work just fine on X2. Also, my worksheets are simply not running right now, and I'm not sure why. Thread pool. Oh, it timed out while evaluating a worksheet at some point, and then it just decided to kill worksheets altogether. I wonder if like restarting the server will do that. No, we just close VS Code. Reopen it. We can be pretty confident about that. And at this point, we won't need precision to multi. I'll just leave that at the bottom of commented out just as a remembrance for now. I could read them. It's evaluating that worksheet, and oh, cool. We have progress. We're having wrong number of parameters. This is a compilation error. Okay. Expected one parameter. Wait, where? So this is a string to vector string. Okay. Indices. A list of indices. Oh, you know what? We never actually did. C, right? C does not exist here. So we actually have to figure out the steps taken. We haven't actually finished implementing this. The indices, is there something, is there an index that is in common with all of these? So basically what we take is causes dot map the indices, and then we just fold that with an intersect. Yeah, dot fold intersect. I mean, they're vectors, not sets, but like, you know, this should work. And then I'm gonna take min option. So val I is that. And then steps taken can be with the I that get else directions dot size. So that's a common index. Okay, I'm still getting a weird error that says wrong number of parameters expected 1. And it's not even telling me exactly where. Mad Compass, thank you for the follow. And welcome to the channel. I think we're on the brink of solving part 2 of day 8. I'm just getting weird compilation error. It's not being very specific. And I mean, I almost suspect. Oh, these are coming from mdoc. So these aren't even in reference really to my code. So mdoc is confused. I think this means like a server restart. That's is actually states. Yeah. Metals restart. We'll restart the build server. It's like mildly. Maybe. Who's going about this? Oh, it was up in there. Okay, and can we take an intersection of two vectors? Vector 3, 4, dot intersect vector 4, 5. Right, vector 4. No, we're just folding this. Fold the remap this to a vector of int. Oh wait, this is a list that we're folding. Yeah, sure, that's fine. The indices, and when we fold this, we should get a single vector of it, right? Now, intersection. I'm just gonna do this. We're just gonna do this much right there. Right, look at the type. And then intersection at main option. Right. Okay. Wait, this fold needs a base. Yeah, we just need the intersection of all of these. Oh wait, fold versus fold left. Yeah, okay, it still needs a base case. Oh, you know what we're gonna do? We're gonna do a reduce. I guess they should. Well, they don't necessarily all have Z indices. Okay, so what would you intersect with that has that intersects just fine with everything? No, I think we do want a reduce. This is assuming at least one of them has a Z. Like maybe that looks. And there's a reduce option in case it can't do it. Okay, let's just do reduce for now. See if that works. And okay, we're getting the right answer for the example case. And add that up pretty quickly. I'll just go to the real case now. And now let's see how long that runs. Right, so if we're not infinite looping on the example, then we should be infinite looping here. If anything, it should just be slow. And I was thinking, it might error out here on the reduce if it happened to be like that they all didn't have any Z indices, but that seemed unlikely. um, but at least we know the logic is right and there are no off by ones that we have to worry about. So it did get 6. But maybe this is not enough of an optimization. So at each step, all we're doing is getting the Z indices, which are cached. So given that start, what are the Z indices? Take the intersection of all of them, and do they have a Z index in common? And if they do, if they're perhaps multiple, we'll just take the minimum one, right? But basically this I here is, okay, if they do, this is an option of int. Is the index that they have in common if they do have one. And that is the number of steps taken. Otherwise, you just go direction, not size. And the new positions will be, you just go into that cached path and take that many steps. Right? And we do this on every iteration of this loop. We calculate new positions and steps taken. And then in our collection, which we know this terminates properly, we collect the first case where all of the positions they are at ends in Z. And the steps that's paired with that is going to be our answer. So reading through that seems to make sense. But I was reading through that partially to assess performance, right? But for each time through the loop, we're looking how many Z indices could there be? Maybe I should look at this. Oh. Wait. Oh, wait. Yes, this is still showing the old one. Yeah, I'd have to end this computation, which has been running for 3 minutes. That's too long. Okay, so let's do some analysis. Let's end this evaluation. And let's take a look at some of these Z indices. Let's do like indices of each. Okay, so a bunch of these have no Z indices at all. DBF has a Z index at 283. Wait, 283. It's directions, not size. You can take at most 183 steps. Interesting. So it has a Z at the end of its path. This has a Z at the end of its path. These all have, when they have Z's, they only show up at the end of the path. So we have a problem here. We're not actually finding all the Z indices. Okay, so let's take a closer look at this. So we're filtering. And there's this thing, and this _1. _1 is the string, right, that it's paired with. I mean, we can make this more clear. So let's just define this in a way that's more clear so we could debug. So map values. So we have path, right? Up here, path.zip with index. And then let's collect cases instead of doing this. So collect case. I'm going to use P. P for precision, I, P that ends with I, and we return that index. And then let's do Z indices. Oops. There we go. Oh, and it's defined twice now. But okay, that's more legible there. And we're still getting the same thing. Okay, let's look at each of these cached paths, I guess. Cached path for each print line. Okay, so MQF goes through, I mean, this is a list of 283 locations. And are you telling me? Okay, so we're gonna take all these cached paths, values. Okay, and then for each of these, we're gonna count dot map dot count dot ends with Z. So for a sec. And this will help us verify. Wow, most of them seriously have 0. So maybe it's our path calculation that is incorrect. Okay. So path, yeah, so given a start of some point, edge.keys iterator, fine. Edge.size, just verify that how many, there's 750 elements in there. Now this path directions at full left. And we start at the start, we have a path and we have a direction, and we move. Let's just look at this with an example. So path of AAA. Okay, so AAA goes to QDM. Well, let's just print the direction line too. Directions. So first we go left, right? Just make sure AA equals QDM. So we go left to QDM. So now we look up, let me just make this bigger on my right side. QDM equals GHX. Yeah, we go left again for GHX. Now we go right twice. So GHX. Then we go right to JGX. I mean, so I'm pretty confident that this path, I mean, I say after 4, but it looks like this is working properly, at least so far. So there's not an issue in our path. And yet, it seems like most of these paths have no Z's. How many even end with a Z? So there are 6 that end with a Z, and they all end on they're all on the right. Or there are 6 right-hand sides and a Z. How many are there that end? Oh, it's always going to end on the right. The Z's never appear on the left-hand side. And there are only Okay, there are only 6 z's. Oh, right. So the z indices, there were not even going to be multiple indices. I mean, that's not the case generally, right? And that wasn't the case for the first one, was it? Um, and wow, if they are all 283, if they really are all 283, then we can actually simplify this logic further. So, let's look at this. We can search backwards from Z until I mean, that's the same thing as searching forwards from A. Yeah. But if it's always 283, then we don't even need the whole path map. We just need to know where a path ends after the series of lefts and rights. And these directions here, there, ends with a right. So that is probably what's going to happen. The Z indices, we printed line, and there are only 3, there are only 6. So we're gonna do like a dot filter not empty. Wait, the second element is not empty. Oh, okay, some of these are 0, precisely because they are the first element. Or, like the element we chose to start with. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Huh. Okay, so we're gonna do this filter and we're gonna count. Okay. And we're gonna count the ones where that contains. There are 12. Wait, there are 12? That does not quite make sense to me because there are only 6 Z's. Maybe like there are 2 paths. Okay, so anyway, these destinations are really all that we need. If it's always going to be 283 and take the full loop. So destinations, dot filter. Oh, yep, exactly that. For each print line to everything that ends with Z at the end of the cycle. And there are indeed 12 of these. And it's like DBF and VBX both end up at XTZ. I suppose that's fair, right? Like they can at some point merge into the same element, right? Like DBF and VBJ might both have a right element that's the same right element. So that's fine. That's fine. That's fair enough. But basically, this states function, we're going to write yet another version. And I think we will also test that this works on the sample case. No, I won't bother this time. So, decision steps, we don't even need to count steps anymore. We just take this first. Yeah. So now that we know that it couldn't possibly stop before that full cycle is over, we don't even need steps. So we have our starts, and to get the next, we just keep doing destinations. So dot map, yep, destinations. And then states dot index where for all. Oh wait, the all was there. For all ends with z. And what do we do that index? Let's say we multiply by 283. Is there enough by one error? Let's say we found it after one movement. Then the index will be 1 because 0 is your A thing. Yeah, so we just take that times 283. Now ends 2. Yes, so that should be it. It's probably still not going to be performant. But now this is a case that is much easier to think about optimizing because there's a lot less moving, right? A lot fewer moving parts. Let's delete some stuff we no longer need. So these z indices we no longer need. Cached path we no longer really need. My explanations are awesome. Thank you. I'm glad you're understanding my code as I go. That's honestly part of why I started streaming, so I get better at explaining what I'm doing as I'm doing it. Okay, so we no longer even really need as in fact here all we need now is the left. So we can do destinations. We're gonna take edge. Wait. Path, what are we applying to? Let me make catch path. So destinations can be edge.keys iterator. Start. And then we do this thing up here. So directions. Fold left from that start, and we're not doing this vector thing anymore. And we're just doing move. Start, move. There we go. And in fact, it's in here. Is that being too concise? But it feels really good to delete a lot of code. So here we have starts, we have destinations, we have all this stuff here. We have states, and then we have our answer. Okay. Don't need that print line anymore. We're gonna go here. We gotta bring up example 2 again. Let's make sure. Oh, this needs to be a map. So this is a list. Keys iterator. Oh yes, we have a start. Give it that name. And then you have to tuple that. Then that to map. Okay, great. Let's test this. Oh wait, not 283. It's gonna be directions. That size. And if the example data follows the same thing, okay, it does, and we get 6. Okay, so we know this works on the example once again. And now I'm running it. It's probably the case that it will run for too long. It's already running for 10 seconds. It's too long. Uh, but we can think about optimization. That's a whole point. Now we can think about like how many cycles away we are from. You know what? We kind of have like the same kind of thing. We're kind of doing the same thing we were doing much earlier, but at a larger scale. So earlier, I was doing all this search down indices, like move by move, turn by turn. Um, and that's where I was first like trying to look for cycles. Now we have that same thing, but it's cycle by cycle. We look for like a whole like cycle of the directions at a time. And now we can try some of those same optimizations that we were performing previously, except at this larger scale. So we can follow the destinations, and given a destination, we could look at how long, how far it is from a z, how many steps from a z. Oh, and then at this point, we can do a Chinese remainder theorem, right? Because now we don't have to worry about the cycles being different each time we do left and right turns. Okay, okay. Let's think this through. Let's do some exploratory search here. So I'm not going to worry about those states right now. Let's take our starts. So it's this list of 6 positions, all ending with A. Excuse me. 6 positions, all ending with A, and I think we want to search through destinations. So like, let's do like an iterator that iterate, starting with, let's say AAA, for example. And then we just apply destinations. And then next square ends with Z. Right. I just kind of want to see this for each of these. So that ends with Z after 61 cycles. But now from whatever position that is, it might have to continue going. Wait, AAA has to go 61 cycles. So had we been, yeah, that's 283 times 61. That's like a minimum possible answer here. And unfortunately, 61 is not going to be a factor of other things. Let's do this for each of these. And in fact, we could just do it one by one. FTA, CPA, Q&A. So we have FTA, Q&A. Make this a little bit smaller. 61, 47, 73, 59. Those are not nice numbers. Um, and I suppose I could like find each of those and figure out where they end up going on that first Z. Um, but we could also just do this for everything, right? So we have so destinations dot keys iterator and we get the index where it hits Z for any of those. I imagine that can come in handy. And then we stop at some point when they all are like I mean, maybe these all have cycles. So for example, what if we did like iterator? Hmm, I suspect there are cycles here. Why do I do that? Why do I suspect? Index where equals a. Oh, right. Um, this index where take another parameter. So just we're gonna drop one and then take the index where, and we can add the one back here. And that's running forever. Okay, so we know that that does not cycle on itself. Let's write this out for the other two. So CBA QMA, EMA GCA. So CMA GCA. You hate today's. Yeah. GCA. But you are finished with today, so you have that to be happy about. I assume you are because you never come in here until you've finished. Wait, did I miss one? FTA, EBA, UNA. Yeah, I deleted QNA. EMA, GCA, AAA. Let's get QNA back in there. I mean, I don't know why I'm doing this. Well, I'm doing this manually because I like to be able to do this. It's clever. It's clever though. Yes, yes. At some point, I'm going to click in my head and I'm going to realize what the trick is. I don't want any spoilers on what that trick is going to be. But Gupta, I can tell you this much. I did finally figure out that it has to be at least 283. So you get a full cycle of the moves, and it has to be at least that unit. So I simplified greatly by like having a map of for every starting position where it ends after a full cycle of all of those directions. And I'm using that to optimize, and then I'm building up on that, and I suppose I have to do like further optimizations at a higher level. And at this point, I'm doing, some exploratory research. Let's see. I'm curious. I'm curious. So find the one that ends with Z, and these better all be like different, right? Not really clever. Without mentioning more things, it's a very hard problem. It's not really clever. Okay, so we have we have some disagreement, but a hard problem, I believe. Hmm. Okay, so they all get to Z's after so and so many cycles. Um, wait, was 61 my answer for part one? 61 times 283. What was my answer part one? Okay, 1 times 283. It's just a check. 17,263. Okay. Yeah, that's interesting. 17,263 was it, right? Okay. Huh. Okay. Now, can we take each of these, for example? Let's take one of these NZ places. So TBZ. Where's the next Z? Oh, okay. What we could do. Oh, hey, that goes with Z. What we could do. All we have to do is think about like where to get the next Z from every Z, right? Or I mean, that's a start. We'll get to Z's eventually. Um, and we still want to keep getting. It's the only thing we can guarantee we will get to. So we can cache. We can cache all of the Z's. What's the distance to the next Z? And maybe we can use those numbers and we won't even have to like simulate doing all the paths. We can just do some math, some magic with the numbers, right? But TBZ, oh, right. Um, drop one, then find one that ends with, right? Like surely that ends at another Z. Oh wait, is that real? Did it end back at itself? Let's look at XTZ. XTZ ends back at itself. TBZ ends back at itself. Um, I'm just gonna do an index where there and make sure it's not like the first index. Index where ends with Z. TBZ. So after 46, it cycles back to itself. Okay. Yes, if they all end up cycling back to themselves, then we're onto something. And then we can just add that, and then now we do some sort of you know, Chinese remainder theorem kind of thing. I keep saying Chinese remainder theorem. My gut instinct is kicking in. Maybe I don't even know what that word means. Maybe I'm just saying it because I know it'll make me look smart. Let's see. Okay, they all loop back to themselves. Okay. Um, this is progress. This is progress. And what are their looping indices? Let's just do an index where. We are coding today, brought to you by multi-line copy paste. Okay. So, 47 plus some multiple of 46 equals 73 plus some multiple of 72. Yep. CRT, CRT. Mm-hmm. Oh, by the way, Hobo Nautilus, thank you for the follow. Welcome to the channel. And Limpid, I missed your follow. Thank you. Okay. Okay, this is straight up CRT. Okay. Pet alligator. Pet alligator. Thank you for the follow. This is applicable here. Um, so we have a constant factor, and then we have some multiple of all of those numbers. So let's start with 2. And then we can generalize. So 47 plus x times 46 is equal to equals 73 plus y times 72. It's great to see Scala. The last time I saw it was a decade ago during my university time. Ooh, a decade ago. You must have been going to university at EPFL. Hmm. Because a decade, well, I mean, I guess a decade ago is 2013 at this point. So it was around. But I mean, as far as universities, I don't know that many had adopted it back then. Okay. But yeah, thank you for the follow. Welcome to the chat. You are seeing on this page right now, Scala, written by a developer with 10 years of experience in the language. Truly magnificent functional programming right here. Okay, math. I need to get my brain to math. Um, so okay, let's read. We're gonna read an article. Myself underneath here. Isabel, thank you for the follow. History statement. Okay. Let n be integers greater than 1, which are often called, okay, these are moduli or divisors. Asserts that if the n are pairwise coprime, these are indeed pairwise coprime. These are very coprime. And if a1 through ak are integers such that less than each respective n, oh yes, so 47, 46, 73, 72, 59, 58. In fact, they're all exactly one less. Yeah, they are all exactly one less. That's interesting. Oh man, this is where I wish I was a better mathematician. So, um, such that 0 less than a less than n. Okay, and there's one and only one such integer x, such that 0 less than x less than big N. What does big N mean? And the remainder of the Euclidean division of x by n is a. A here being like the z periods. Okay. So we can call these up on top. We can call those the z starts. And then these down below, the ones that are all just one less, we can call them the z periods. So rephrasing that in terms of this, so we have z starts that are all all coprime, and then we have z periods that are less than that. Of all n. Wait, what is big N? Let us denote n. Let's denote by n the product of all the n. Oh, okay. Thank you very much. Thank you very much. One integer less than the product of all the n. So there's only one x that's less than the product of n, and the remainder of the division of x by ni is a. Okay, so the divide x by each respective ni. Ni in this case being are z starts. Divided by the z starts, yeah, is the z periods. And then we can look at the congruences. Okay, so x congruent to all of these. Right, and x will be the number. Okay, so if we have a number that's congruent to each of these, okay, so we have a number, let's say we have a number that's congruent to all these a's. Congruent to 46. Right, congruent to 46, which means, this is the thing that we keep repeating. We keep adding another 46. Oh, wait, we want it to be congruent to this, don't we? No? Mod n. N is our start. Okay, no, this is right. Because a is less than n. Yeah. So x is congruent to 46 down here. Right, I got that backwards. 46 mod 47 is congruent to 72 mod 73. Okay. That system has a solution. Any solution, say x1 and x2, are congruent modulo n, as x1 is congruent to x2 modulo big N. Okay. If they are co-prime, then the map defines a ring isomorphism. Okay, well, thank you. I'm not. It's been at least a year since I've been reading up on any kind of abstract algebra. X by there's one and only one integer x. And how do we find x? The remainder of the Euclidean division of x by. So we keep adding 46, and it's. I'm gonna take all of these and multiply them. In fact, let's start getting these. So let's take starts dot map. I take code much like this here. And this would be val z starts. Yeah. Okay, and then val z periods. Is shift these here. Okay, so drop one index where, oh wait. Start. And we do the best of a start. So it still starts map destination map dest. And we keep mapping on destination. And ends with z. But this is a problem where we had to notice a pattern in the data, right? Oh, arrow. You check the periods for each repetition. Yes. The periods were listed out here, right? So these are the z periods, and these are the starting locations of each of those, which is one greater than a period. Oh, which is also to say, like, you know what? I'm just gonna multiply all these together. Yeah, I mean that's an answer. But I guess what this is saying is there's some x less than n, which would be the product of all of them. I'm not sure. String. Um, and then we start at destination. So 4773. Oh, wait, we're getting different numbers now? 4571. Here we had gotten. Oh, wait. Index where? Oh, hold on. We did a drop one, and then we did an index where, and then we didn't add that index back. So it's exactly the same. It's exactly the same. Oh, you know what? This makes so much sense now. This is why we had 12 ending up at the Z. Um, FTA goes to exactly the same as TPC in the same amount of time, which means they probably share most of the path. I bet if I did look at the path, they both essentially go to the same. Okay, let's look at that. FTA and TBZ. FTA equals MHG CRF, and then TBZ. TBZ equals CRF and MHG. Yes, they do it in opposite order though, but they are the same things. Okay, so here we do a +1, and so okay, now these are exactly the same if you add the +1. So in fact, I'm just gonna take the starts dot product, and these are all. Are these all prime numbers? These are all prime numbers. So there's no point in finding like the lower common whatever. So starts dot product times that too long. I'm worried about that. Starts dot map. I'm not worried about overflow. Too long. Product times 283 long. A for math. Um, wait. Oh no. We don't want starts. We want periods. Whoop. Okay, so this is these starts. Okay, let's try that. Yeah. Yeah, and the least common multiple is just gonna be the multiple because they're all prime. 146 316 047 596 49. I don't know why I insist on treating that like authenticator code. There it is. There it is. Okay, we got it. Yeah, I don't know what I call it. So we're just gonna call this periods now. Um, and let's delete the stuff we no longer need. Okay, you know what? I like this problem. I like this problem. For a few, I mean, like, it's use math. I kind of took a detour there. It took me too long to just be like, okay, let's just multiply the periods or whatever. But I liked that there was like an exploration element. You had to sort of notice a pattern in the data. And ends one can be simplified as well. um, I don't know. We do this. This is ends one, and we can remove what? Move. I'll clean it up after. So this is what I'm gonna commit. Oof, the actual problem is very hard, but whatever. Yeah, I I like the problem. I enjoyed that. Hmm, hmm. All right. Let's see how I did. This is a day where maybe people gave up on part two. I can imagine people getting up. Oh, I still ended up rank 8,000. I need to stop looking at this page. I already know I was not that. Mm, okay. Wait, a lot of people. Okay, a lot of people did finish it. That's good. That's good. Um, this board is a little bit more sparse. I'm temporarily on the top. Jan Peter at some point will figure this out. Oh, Alexandria. Hmm. Like, if each source would go through multiple of the Z ending things, then you have to check a lot more stuff. Yes, yes. Here, each of them was just paired up. Yes, yeah, like that full generalized problem would be much harder, and that full generalized problem is what I solved at first. But of course, that was never going to be efficient enough, right? So I had to iterate on solutions until I noticed that pattern and then solve that simpler problem. But I had to notice a lot of things to get there. Hmm. Okay. Well, I could. I'm just gonna clean this up tomorrow, as part of my warm up. I'm pretty happy with this. Again, I'll just make my GitHub if anyone wants to join. Um, if you're on YouTube, this stuff is down in the description. And what else? This is a leaderboard. If you want to keep pushing me further down, I have fallen down to 8th place. And you can show me your skills and give me something to shoot for. And what else do we have? Yeah, that's that. If you want to share your solutions with me, which I'd very much love to see your solutions, you can come over to the Discord and post it in the admin code channel there. And if you post your solution for today before tomorrow, then I could probably start the stream by reviewing the solutions and stealing your ideas for the future, making myself faster. Uh, and again, on YouTube, that's on the description. Let's find someone to raid. So, which advent of code? Who is still on? GG Impact is still on. GG is almost certainly done though. Like I don't recognize a lot of people right now. Let me look at who I'm following. That is on right now. Oh, there's a lot of other stuff. Honestly, I think it is Chi Chi tonight. Let's raid Chi Chi. It looks like people maybe people either finished or went to bed and gave up. It's seems like a smaller night. All right. I'm gonna pop into his stream and I'm gonna start a raid here. So, wait, where is he?
It's more like build an app. Okay. Oh, okay. Got it.
All right.
Right.
Oh, I go cough myself to death.
Okay. Great. So let me.
Thanks, everyone. Have a good night and good luck with the rest of Adam and Code. Looking forward to seeing more of all of you.
Display capture.
say hi to
Okay, let me
Chi-Chi.
just make sure. Okay, pending. Okay. Cool.
All right.